Good evening from Munich. My name is Sebastian Ohlmann. I'm working at the Max Planck Computing Data Facility in Garching, which is the central computing center of the Max Planck Society. So the Max Planck Society is Germany's largest basic research organization. And today I'd like to present work that I did together with Fabio Baruffa from Intel and Markus Rampp, also at the Max Planck Computing Data Facility. And I'd like to talk about overlapping communication and computation using Intel MPI libraries, asynchronous progress control. So why are we interested in that? What's the motivation? Well, if you look at scaling, if you scale codes to larger node numbers, then quite often communication time can become a bottleneck. And one way to get around that is to overlap communication with computation, because then you can hide some of this communication time. Usually this is implemented with non-blocking MPI codes, but something that one might not be aware of in the beginning is that communication is not progressing asynchronously if one just uses non-blocking MPI codes. But the progress is only happening when some function like MPI test or MPI wait is called in the end. And now the promise of Intel MPI's progress control, what makes it interesting is that the progress is asynchronous and it's handled internally. So there's no change to the user code needed. And that's of course quite nice, because there's the promise that it can become faster without you having to change your code really. The implementation in the user code is in principle also possible, but there you need quite some changes. So there are different strategies and they're well known, but you need to change the code in some places, and there's also quite some experimentation of how to do it best. So you can, for example, add some codes to MPI test and the computation loops, but this requires quite some changes. And so in this project, our goal is to evaluate the Intel MPI's progress control feature. So how does it work? In Intel MPI's asynchronous progress control, progress threads are spawned for each MPI rank, and they drive the communication. There's support for different operations, for point-to-point, for blocking collectives, and also for non-blocking collectives, but only broadcast, reduce, and reduce. It's only available in the release MT and debug MT variants, and there are few environment variables that you can use in order to enable it basically, and also to control the pinning. So the goals of the study are, as I already indicated, to evaluate this feature of the Intel MPI library, the asynchronous progress control, for real application. And the reason is that the documentation is quite often quite sparse about these asynchronous progress features. And moreover, the examples you can find are often just for test codes where it's not so clear what is the benefit maybe for a real application. And to do this, we wanted to find the best configuration. And for this, we always compared full node runs to get the fastest time to solution. So using full nodes, either with or without this asynchronous progress control, and then to see what is the fastest we can get. And then also we have a hybrid code, so it's also interesting to see what combination of MPI ranks and OpenMP threads is the fastest. And also, do we need spare cores for the progress threads, which means that we would need to kind of sacrifice cores that you could need for compute for the communication. And then this, of course, is relevant to see, does this then make the code slower or faster? And also is pinning necessary. And yet, I will say a few words about how to generalize those results to other codes that are similar in the operations. Okay, the application that we used is Octopus. Octopus is a density functional theory code with pseudopotentials. It has a real space grid, and it uses finite differences for the operators. So it's a Stencil code, and it's mostly used for real-time time-dependent calculations. It has a hybrid parallelization that uses MPI and OpenMP, and it's mainly a fortran code which also has some C++ and some CUDA for GPU support. So all the tests I did here without the GPU support, but only on CPUs. And how do we overlap computation and communication here? Well, we do the communication of the boundary and ghost sets while we do the computation of the inner part of the stencil. So I draw this little figure here on the right-hand side where you see a sketch for a 2D example. So the blue points basically are the points that you're interested in, the local points in the domain decomposition. And then those are the boundary points that need to be communicated from the neighboring processes. And now the inner part here are those points where the stencil doesn't touch the boundaries, so they are independent of those boundary points, so they can be computed while the boundary is still communicated, and that's where we can really overlap computation and communication. To make this a little clearer, I made this plot here. So this basically shows you the time and what operations happen in one time step. So time flows from left to the right. The red parts are communication steps, whereas the blue parts are either copy steps or computation steps. So let's start at the left-hand side. So what we do is we gather the points for the communication, which is kind of a packing operation, and then we start the non-blocking communication for the ghost points using iReceive and iSend, so non-blocking point-to-point functions. Then we do another operation that's not so relevant here, but then we have the inner part of the stencil application. Then we wait for the communication to finish. And then we do the outer part of the stencil. And in this part here, we can basically overlap the communication we need for the ghost cells with this operation here and the inner part of the stencil. Moreover, in addition to that, we have an ORReduce function that we use as a non-blocking collective, and that can also happen in parallel over here. So those two things are basically where we can get the overlap. Okay, so let's see what clusters we used for the benchmarking. Two clusters that we have at MPCDF. The first is called Cobra. It has Intel Xeon 6148 Gold CPUs, so Skylake architecture with 220 core sockets per node, so it's 40 cores per node, and it uses an Omnipath network with 100 gigabit per second, and we have around 3,500 of those. And then the next system is the newer Raven system, which has been installed just a few weeks ago. It uses Intel Xeon 9242 Platinum CPUs, so Cascade Lake AP, where we have 248 core sockets per node or 96 cores per node. And here we have an Infiniband HDR network, also 100 gigabit, and we have around 500 of those nodes. Moreover, the memory bandwidth is a bit better for those compared to the older Skylake nodes. Just for reference, this is the system that we're looking at. So it's a silver tip over crystal, and this is mostly for reference for you to compare later for people who are more into the topic. Okay, so now let me show you some results from the benchmarks I did. First, some explanations for the labels in the plots you will see. I will compare three modes. The first is called sync, where you have no asynchronous broker, so it's just the code as is with the MPI library without the asynchronous brokers feature. Then we have async, where we use asynchronous brokers threads, but these brokers threads are not pinned, which means they run wherever there's some spare place in the operating system, basically. And then we have async pin, where we use asynchronous brokers threads that are pinned to certain cores. And then I compare different combinations of MPI ranks times OpenMP threads for hybrid parallelization. And for the cobra nodes, for example, full nodes would be 1 MPI rank times 40 OpenMP threads, or 2 MPI ranks times 20, and so on and so forth. When we use dedicated cores for the brokers threads, we would, for example, sacrifice some of the cores. So we would have 1 times 39, or we would have 2 MPI ranks with 19 OpenMP threads each. So in this case, we would sacrifice 2 cores for the brokers threads and just use 38 for compute. Pinning was done using srun's CPU mask just for completeness. So now these are results for runs on Cobra, which has 40 cores per node and on 60 nodes, to see what is the best combination in this hybrid space, basically. And there are 2 things that you can see here. So these are the 3 different modes. So the first is that using asynchronous progress is not always beneficial, but quite often. And the fastest run of all those is always with using asynchronous progress and with using pinning. So the 4 examples on the left-hand side are the ones where we don't use all the cores for compute, but leave some empty. And on the right-hand side, we use the full node. And so you see, if we don't have dedicated cores, we get resource contention when pinning is enabled, and that's why it takes quite long. So the y-axis is the time for the run. And you see that in these cases, basically you shouldn't use pinning for the asynchronous progress threads if they're not on dedicated cores. If they're on dedicated cores, this option is the fastest. And this is also true for all, for running on more nodes. So here I did some scaling up to 128 nodes. And you see that the fastest option is always the green one, which here corresponds to async pin, so including the pinning, and also some dedicated cores for this. And you see that the speedup is also still there at 128 nodes in this example. And the speedup is plotted here. So this is the speedup compared to the synchronous case, and it's about 1.03, sorry, to 1.06, so 3 to 6%, which is not, huge, but still it's basically you don't have to do anything to get it, more or less. And then if you look at the scaling, you see that the scaling is similar for the 3 cases, and the efficiency is still at 84% when going from 16 to 128 nodes. So this is basically the parallel speed up compared to the run at 16 nodes.
Sebastian, can you quickly wrap up?
Sorry, can you repeat?
Can you quickly wrap up?
Oh, I only used 13 minutes up to now, I think. But if you want to, I can speed up a bit. Because I think we started 2 or 3 minutes late, but yeah. Okay, so then let me go a bit quicker through the results for Raven. They're quite similar. You get the fastest runs with pinning and dedicated cores. The speedups, as you can see in this plot, are larger than for the other system. The speedup here again, compared to the synchronous case, is about 17 to 20%. So that's already quite sizable. And there are 2 main things that are different between the systems. One is that Raven has a higher memory bandwidth, and the other is that it uses Infiniband, but it's not yet clear really what is the reason why it's faster. Okay, the scaling is still quite okay. So let me go briefly to how to quantify the overlap. It's actually, you would like to know basically in which sections of the program you really gain something, but it's difficult because we have quite a strong imbalance in the communication volume here. And that means that we cannot really compare the different parts during a time step, but we can compare the average time in MPI functions. And we see that this is reduced from 40.8 seconds to 33 seconds when using the async pin. So even using asynchronous progress threads and pinning. And this means that we can really reduce the time spent in MPI functions due to overlapping the communication with computation. How can we generalize this to other codes? Well, you need to split the stencil in an inner and an outer part. The benefit for other codes then might be similar. It depends a bit on the stencil size. So we use a 25-point stencil here. And probably hybrid codes benefit more because in this case, you need less cores that you need to spare for the progress threads. on Cobra, for example, 8 times 4 was the best combination in most cases, which means we have 32 cores for compute and 8 for the broker threads. And this is probably not even so bad for codes that are anyway bound by the memory bandwidth, where you can already saturate the memory bandwidth with 32 cores. Okay, with this I'd like to conclude. So in the evaluation, we found that Intel MPI asynchronous progress control really allows overlap of computation and communication, and you don't need to change your code in order to use that feature. Of course, only if you already have that overlapping implemented using non-blocking calls. The speedup we got was around 5% on Cobra, around 20% on Raven. And the lessons learned are you need to use the MT version, so the multi-threaded version of the library, and you need dedicated cores and correct pinning, and the best potentials for hybrid codes. With that, I'd like to thank you, and I'm happy to answer questions either here or in the Slack channel.
Yeah, we have asked some questions on the Slack. You can answer on the Slack channel. Thanks
Okay,
for
great.